Hello and welcome back to the third and last part of the untyped lambda calculus. In the last two videos, we hopefully gave you a basic understanding of what the lambda calculus and in particular a lambda term is, and how computation works. In this video, we want to actually construct functions and numbers in the untyped lambda calculus. We're also going to explore what class of functions we're able to construct with the untyped lambda calculus and what its limitations are. There are only three rules to construct a lambda term: the variable rule, the application, and abstraction rules. This might seem like it doesn't give us a lot to work with, but these three constructs are enough to define numbers, arithmetic operations on numbers, a way to represent boolean values, so true and false, a way to represent basic control flow in the form of if and else, and a way to represent recursion, which allows us to achieve Turing completeness. Let's start with defining natural numbers in the lambda calculus. You're probably familiar with the way of defining the set of natural numbers by induction. We say 0 is a natural number, and for every natural number n, its successor is also a natural number. So the basic idea here is to start with 0 and to count up by continuously applying the successor function. With function application and abstraction being the fundamental building blocks of the lambda calculus, we can do something similar. We define a number as a lambda term with two arguments, f and x, and the term for the number n then applies f n times to x. This way of representing numbers is commonly referred to as church numerals. It's named after Alonzo Church, who was the first person to encode numbers in the lambda calculus this way. As you can see, to construct a 0, we have a term that depends on f and x, and just returns x, without applying f at all. So in other words, it applies f 0 times to x. Then to construct the number 1, we have a term again with arguments f and x that returns f applied to x once. For 2, f is applied twice, and so on. An important thing to understand about church numerals is that the number is the term. It represents the action of applying any function n times to any value. The function itself and not the result of the function is the church numeral. We're mainly going to denote church numerals by c with a subscript n, so cn instead of writing out the whole term, and if it's clear from the context, we might also just write down the number n in a lambda term. With that said, let's look at some common arithmetic operations. These are the lambda terms for the successor and predecessor functions, and for addition, subtraction, and multiplication. Together, we're going to prove that the successor and addition functions work as we expect them to. The remaining three will be left to you as an exercise. Before we get to that, a quick note on the predecessor function and subtraction. The church numerals on which these functions operate only construct natural numbers. This means that there's no negative numbers. In particular, there's no predecessor of 0 or no minus 3 as the result of 2 minus 5. But the predecessor function and subtraction are defined in such a way that those cases where the result would be a negative number, it always returns 0. So the predecessor of 0 is 0 again, and with subtraction applied to 2 and 5 is also 0. Feel free to apply the functions accordingly and to confirm this for yourself. Okay, let's start with the behavior of the successor function. The successor function takes a term m as an input, and this will be the variable for the church numeral for which we compute the successor. The remaining term looks very much like the second church numeral. F is somehow applied 2 times, and x is at the end of the application. To confirm the functionality of the successor function, we're going to apply the function to a church numeral cm, and test whether it returns cm plus 1. By alpha convention, we have to make sure that the names of the free and bound variables differ, and also that the bound variable names don't overlap. So we can't use the church numeral definition with lambda f, lambda x, and the successor function as written here, as we would use f and x bound twice. So we change the names of f and x in the church numeral to g and y. To start the computation, we have to choose a regex to contract. At the moment, there's only the m regex with the church numeral as its argument. If we contract this regex, we need to substitute every occurrence of m by the cm term. In our first few computations, whenever we do a substitution, the term or variable that is substituted will be highlighted in the line before, as well as the term that we substitute it with in the line after. So this time, the m will be substituted by the cm term here, so we just put it at the spot where the variable m was. Now we should reduce the regexes of the church numeral, starting with a g regex. We need to substitute the g to the power of m by f to the power of m. Don't forget that this exponent is only a short form for applying g, or f for that matter, m times. And continuing with the y radix, we substitute the variable y by x. Now this already looks quite similar to the church numeral term cm plus 1. We have a term depending on f and x, and we apply f to f m times applied to x. So we actually apply f m plus 1 times, and therefore we have the m plus 1th church numeral. To put it simply, to get from applying a function m times to applying a function m plus 1 times, we just need to apply the function once more, which is exactly what the successor function does. Next up, we're going to analyze the term for addition. To do something m plus n times, we need to do it m times, and then an additional n times. The inputs m and n will be the church numerals again, and for the sake of readability, we're going to stick to the symbols cm and cn for now. First, we need to substitute every occurrence of m by cm, and then every occurrence of n by cn. After these two steps, we reach this term. Here, we can't see any radixes to reduce, but there are some in the church numerals. To reduce cnfx, we need to write out cn. So we insert the whole term while making sure to only use valid variable names. Now g is once again substituted by f, and y is substituted by x. Lastly, we need to reduce the radixes in cm, so first, we have to write out the term. And then, substitute h by f, and z by f n times applied to x. In the end, we get the following: f m times, another n times, and then the whole thing applied to x. So, by adding up, we can see that this whole computation yields f m plus n times applied to x. This is the m plus nth church numeral. So, we've proved that the successor function and addition work on church numerals just as we expect them to do. To check the functionality of the other three terms, you just need to follow the same pattern. Apply the terms to church numerals, compute them, and then see whether the output is what we hope to achieve. Next up, we want to define booleans, and with it, if then else conditionals. So, we want a lambda term that, if some condition, let's call it b, holds, returns m. Otherwise, it should return n. The b will be a boolean value constructed as a lambda term. M and n will be arbitrary lambda terms. And this conditional will be translated into the application b applied to m applied to n. So we need to construct two terms for this b. If it's true, it should return its first argument and its second argument if it's false. With all the tools that we've defined so far, this can be done quite easily. Feel free to pause the video for a second to try it out for yourself. The term true takes two inputs, x and y, and returns the first one. So, as a lambda term, it's lambda x, lambda y dot x. False has the same inputs and returns y, so it's the term lambda x, lambda y dot y. Let's quickly confirm that this works as we intended. We should all be a bit more familiar with such computations by now. As you can see, for the term true, we have to substitute all occurrences of x by m, and we get the term lambda y dot m applied to n. In the second reduction step, we would have to substitute all occurrences of y by n, but there are no occurrences of y to substitute, so in the end we just get the term m. The computations for the boolean false are quite similar. This time, nothing changes by reducing the x radix, as x doesn't occur in the term, and we just return the second argument n. So these two terms actually represent the behavior of boolean values in an if-then-else conditional. Another nice thing we can do with booleans is to define the classical logical connectives and, or, and negation, as well as some predicates over numbers that will be useful later. All three logical connectives use the boolean values that we just defined, f and t, and we're going to try them out with some examples. Starting with the operator AND. False and true should reduce to false, so we apply AND to f and to t, and we execute the computations to confirm this. Remember, true takes two arguments, and it returns the first argument, whereas false returns the second. Now, if we write AND out, we get lambda x, lambda y dot xyf applied to f and t. Reducing the two radixes, we get the term false applied to true, and false again. As we know, the false returns its second argument, so this reduces to false. Now, if we compute AND applied to true, true, we get true applied to true, false. True returns its first argument, so this reduces to true. In general, we can observe that the term will always behave in the way we expect it to. Whenever the first input is false, the term should reduce to false by definition of the logical operator AND. In the term, this first argument false is applied to whatever the other input was, and to false. As false always returns its second argument, the term therefore will always reduce to false. However, if the first input is true, we will return the second input, which is true if and only if both inputs were true. So this lambda term basically tells us to only look at the Boolean value of the second input if the first one is true, since we'd already know that we should return false if the first input is already false. Moving on to the second operator OR. We can see that the first input value again decides how to proceed. If we compute OR false false, we get the term false true false. As false always returns the second of its inputs, the result is false. If the first input is true, it returns true without considering the second input at all. So here the behavior is basically mirrored. This lambda term tells us to only look at the Boolean value of the second input if the first one is false, since we already know that we have to return true if the first input is already true. Lastly, let's look at negation. The term only has one input x, which is applied first to false and then to true. So if we apply negation to true, it becomes true applied to false and true, and so it returns false. If we apply negation to false, the term would reduce to false, false, true. And since false returns its second argument, it's true. These connectives have all been fairly easy, and with the foundations that we've built, it's going to get even easier to construct more complex functions. For example, predicates like is 0, less equal, or equal. Again, let's quickly check their functionality together. The function is 0 returns true if we put in the church numeral 0, and false if it's any other church numeral. Is 0 applied to C0 looks like this. As there's only one radix to reduce, we do that, and we have to substitute this one occurrence of n by the C0 term. Since application is left associative, we reduce the f radix next, and we have to substitute f by lambda x dot false. But since in the church numeral for 0 we apply f 0 times, there's no f to substitute, and reducing the corresponding radix only makes the input disappear. Now we're left with the identity function and input t, which reduces to t. So is 0 applied to 0 reduces to true. To confirm that this doesn't happen with any other church numeral, let's test it out for 2. Is 0 applied to the second church numeral looks like this. Reducing the n radix puts the church numeral in front, just like with 0. But here's the difference. Now the variable f does occur in the term 2 times, so reducing the f radix, we substitute f by lambda x dot f. And then x is substituted by the second input true. Lambda z dot f is a constant term returning f, so lambda z dot f applied to true reduces to false. The same holds for lambda y dot f, so the term in the end reduces to false. Since 2 is indeed not 0, this is correct. This works because we only get rid of the constant false term if we have no f in the church numeral, which only happens if we compute is 0 for the church numeral 0. If the church numeral contains an f, we'll keep the constant false term when reducing that radix, and in the end we'll always return false. Continuing with the second predicate, we look at less equal. The analysis of this term is also quite easy. The term takes 2 church numerals as its inputs and checks whether m minus n is 0. Here it's important to remember that the subtraction term never returns something smaller than 0. If the result of m minus n is less than 0, the subtraction term returns 0. Luckily, we've already constructed and checked the used functions is 0 and subtraction. We have the following 3 cases. If m is greater than n, m minus n is greater than 0, so the term sub mn will return some church numeral unequal to 0, and the function thus returns false. If m is equal to n, we know that sub mn is 0, and we return true. Lastly, since we know that sub mn is always 0 if m is smaller than n, the return value is again true. Finally, we look at a predicate to determine whether m and n are the same church numeral. Just like in classical mathematics, we check whether m is less equal to n and n is less equal to m. If both hold, m and n have to be the same. Since we've already proved the functionality of less equal and the conjunction, the functionality of the equality term immediately follows. With this, we conclude the first half of this video, and we're going to continue in the second half with a way of defining functions recursively in the lambda calculus.